Okay, so what is the world hour record? The world hour record is one of the most prestigious cycling record that there are. Where a cyclist, I bet we all know about it, but is where a cyclist is meant to cycle around the velodrome for 1 hour, trying to keep the highest possible velocity. And the reason why this record is so special is that all the best technology comes to play a role in order to have the best and the fastest configuration possible for the cyclist, but also for the whole equipment. So we're speaking about bike, rider position, but also helmet, shoes, fork, suit, every kind of part that aerodynamically can play a role. The start of the race is stationary, meaning that the cyclist starts from zero speed. And many people attempted actually to put their hands, let's say, on this record, many professionals and top athletes in general, but it's quite hard. It's not that easy. We will go through a little bit of a history about this record right after, and also will explain why the latest attempt was so special and so important. Our CEO, Filippo Ganna, was the principal aerodynamicist of INEOS, and his role was quite central into managing the whole aerodynamic of the competition. He was supposed to lead the aerodynamic development of each part, of the design of each part, and of the optimization of the position for Filippo, but not just doing that with every single component of the team, every single team member and company that participated, but also putting all these results together and make sure that they helped each other, contributing to a better performance rather than playing against each other. So when I'm speaking about what parts and what components can be optimized, I'm speaking about helmets, visor, suit, the bike itself, of course, and the front fork, the handlebar, the wheels and the tires, the shoes that are used, and in particular, of course, the position of the cyclist. But there's a lot that can be done there. But let's make a little bit of a step back and let's see why aerodynamics is so important for this competition. Aerodynamics is very important because it's one of the main forces that act on the cyclist while attempting to keep his speed as high as possible. So what are the forces in general that act on this system? The first one, of course, is the propulsion. So it's the energy that the cyclist put from his leg onto the pedals in order to generate speed for him to run faster and faster. The second main force acting against this propulsion is actually the drag force, so the aerodynamic resistance that the flow the cyclist is moving through, which is air, is acting on the cyclist. This drag force is, in particularly speaking at a certain speed, is way bigger than the rolling force, the rolling resistance that the ground act on the bike itself. Then, of course, we have the acceleration as well. But in this sort of race where you're supposed to keep the speed as constant as possible, the acceleration plays a role only in the very first seconds of the challenge itself. Then we have gravity. Gravity as well, when you climb up a mountain, is very important. It's a force that you need to overcome. However, in the velodrome, we are running on flat, and the gravity is definitely not playing a big role at all. And then there is some internal friction, which is almost negligible when it comes to this system. We're speaking about the friction of the different mechanical parts that put the bike in motion in general. Again, another force to overcome normally is the braking force, but in this competition, this is a side problem, is negligible at all. The cyclist is not supposed to use the brakes, if not at the very end, after the race. Once we look into this sort of configuration, we understand that especially at high speed, the aerodynamic resistance is over 90% of the whole force acting against the cyclist when it comes to trying to go as fast as possible. So this is the reason why we are focusing so much into reducing the aerodynamic force with all parts possible. So how can we make sure that we are going to be actually the fastest? Of course, the cyclist plays a big role itself, meaning that the training, the alimentation, the talent of the cyclist himself, of course, have a very big impact on the performance. but the whole development on the side, especially when it comes to riding at a certain speed, at the fastest possible speed for 1 hour, plays a really big role as well into allowing the athlete to achieve his best performance. So for 1 hour straight, we cannot just focus on aerodynamic as well, but everything needs to be compromised with the mechanics and the physiology of the whole cycling performance, meaning that we need to allow the cyclist not only to be as fast as possible, but also to keep a comfortable position that allow him to keep going for 1 hour straight, which is not that easy. But everything else is basically meant to be optimized from an aerodynamic perspective. When I'm speaking about everything else, I mean the helmets and the visor. Both things play a role. The skin suit, of course. In this specific case, we were working with a BioRacer, and BioRacer developed new materials, a new concept to design the optimal skin suit. The seat as well plays a role. The seat is one of the key components to enable comfort for the cyclist. And it also can be optimized aerodynamically speaking, which might sound a bit weird, but we can get some aerodynamic performance out of the bike seat as well. The handlebar, of course, is one of the first parts exposed to the flow, so it plays a role, plus the position of the hands themselves deviate the flow that will go and impact on the rest of the body and the bike, which means that we must be very careful in that area. Of course, we have the wheels as well. In this case, we were working with a Princeton for a perfect fit. The fork and the frame was completely redesigned by Pinarello. A big part of the development was done here as well. The shoes play a role as well. Depending on the cyclist, this is a very tailored development, of course, but depending on the cyclist, we can get up to 3% of aerodynamic improvement just because of the shoes. And the biggest component of all is, of course, the position of Filippo in this case, but the position of the rider in general. If we look at the composition of the biker on the bike itself when they run straight into the air, so they get hit by the wind, we can see that most of the figure of the shape that we are actually exposed to is the cyclist itself. Hence, we must focus on getting the most performance position if we want to really reduce the aerodynamic drag. But how can we make sure that we are actually the fastest? So when it comes to this sort of competition, we cannot just develop the best that we can do and hope is going to work. Of course, we're competing with other companies and other cyclists that try to do exactly the same just a few years, if not months beforehand. So we must make sure that also when it comes to the technology we have available, we use the best we have in also to ensure the success of the whole challenge. As I said before, the cyclist of course plays a role, but the way that we approach the problem and the methodologies we use can actually make the difference between succeeding and not succeeding. In this case, it's up to us, of course, to speak about the aerodynamics and not the rest, but specifically speaking of the topic, we were able to actually have a completely decentralized development when it comes to aerodynamics. So we were not taking care of everything by yourself. We were actually able to allow every part that played a role in this challenge to use some CFD, run some simulations, do part of the development and experiment on some designs by themselves, rather than actually centralize everything and having to slow down, of course, because only a few people are allowed to use the tools. The methodology we used in this case in particular was actually, as I said, allowing everyone to launch simulations and then putting the results together, running some validation on the whole thing, then moving to the wind tunnel only when we had already some sort of final answers, validating everything in the wind tunnel again, and at that point moving to the track. And on the track actually, again, validating the results with some real life experience. This cycle, CFD, wind tunnel and tracking, happened a couple of times. So we went through the cycles first, and then before the final race, everything went through CFD again and then wind tunnel. And then we had the day of the competition. Okay, so we went through a little bit what were the main improvements when it comes to technology and CFD in particular for this record. But if we look at history, the first officially recognized world hour record was back into 1876. And then there have been like a few rule changes and stuff like that. So with the same configuration, the same rules that we use today, the first record tracks back to 2014. But actually, before this attempt, the previous record that was set was in 2019 by Victor Campenaerts, Belgian guy. After Victor, other 5 attempts were listed. All of them failed between 2019 and 2022, especially because of the reasons that I told you before, meaning that you need to find the best cyclist possible to run the race, but most of the time that's not enough. You need to have the technological support to the cyclist, both in terms of aerodynamics but also in terms of comfort, so physiology. 5 attempts have been tried and failed in a span of 3 years, and then we get to August 2022 exactly, when then Bingham, part of the team INEOS, attempted the record and broke it, setting the new record to 55.548 kilometers per hour. The previous record was 55.089, meaning that there is almost half a kilometer per hour more. This is amazing. Then Bingham was part of INEOS Granadier team, and he was working already with Filippo Ganna, which was meant to set the record as well, just a couple of months later, 3 months later actually, in October. Why this is amazing, the fact that Filippo 3 months later was able to set the record at more than 1 kilometer per hour more was amazing, because he of course is a great cyclist, but at the same time the team was working basically with the same technologies, and having some changes in 3 months time of span was not easy. Everything needed to be tailored again onto a new cyclist. Multiple things stayed the same, but many actually changed, and there was a lot of pressure as well, both on the team and on the cyclist, in order to achieve it, since the team was actually the same, so they all knew everything, and being better and trying to improve in this little span of time is not that easy. But Filippo managed, and the new record, the latest record so far, is set to 56.792 kilometers per hour, held by Filippo, part of the INEOS Granadier team. The moment has come to draw the conclusions, let's say, of this webinar. And we want to leave you guys with just a few key takeaways for the further aerodynamic developments that you might want to take on for the different parts of the bikes or the riders that you guys are working with. Main takeaway is that key to achieve this result was to test as much as possible, to be creative while designing stuff, to have some tools that can give you an initial idea of what direction is best to follow, but to be able to test as much as possible and as fast as possible, of course. Always checking if you're following the right direction, meaning that you're not getting deviated by something that you think is working in a way, but in the reality of the facts, the behavior of the flow is different, is key to not get, actually to not lose time and not follow the wrong path. Second key takeaway was that things need to be planned on the athletes most of the time. So if you're really chasing those top results, top of the performance, if you deal with most performing athletes and you want to see some changes and some improvement, you need to take into account the fact that every rider deserves attention for the parts that are meant to bring him to succeed. There's a lot that can be adjusted when it comes to the handlebar, to the position of the hands that the rider is having, as I said before, for the flow impacting the rest of the body. With the skin suit, with the shoes as well, with the seat, the position of the rider, let's not even get into it. But there are many things that have been proved to be working with some cyclists, bringing the results to a 50% improvement, and then the moment that the same solution has been working with someone else showed no improvement at all, almost. Always trade off, third key takeaway, always trade off between biomechanics and aerodynamics, meaning that you cannot think about doing something that works 100% as its best for aerodynamics, and then in particular if the cyclist is meant to ride for an hour long or not, if not more than that, he cannot hold that position well, or not be sitting on the seat in the right way or stuff like that. Fourth key takeaway, test multiple positions digitally first. Digitally speaking, we have the possibilities today of 3D scanning a rider and then adjusting his position in a digital way, which basically means that we don't need to have the whole team of riders or the rider and his whole team behind being in the same location in the wind tunnel to start testing things first. We can do that digitally from wherever we are in the world, and then just go to the wind tunnel when we have already some positions in mind, some things to validate, and a few questions that of course come out all the time that we can just improve on. And the most important items, and I want to leave you guys with this, most important items to focus on when it comes to aerodynamics is the clothing, the bike, front fork, wheels, everything connected to the bike, and the helmet as well. The helmet is very important, not just for aerodynamics, but also to allow ventilation on the head of the cyclist. Increasing their comfort during a long performance can definitely impact on the final results. Okay, so here we are. Basically, this is the interface available to everyone online to launch simulations on AeroCloud. This is what we used for our simulations. So in this case, I'm just gonna get a model to upload quickly. As you can see, it works both with STLs and OBJs. In this case, I'm using STLs. Okay, so here we have the model. As you can see, there are different colors for the different parts uploaded, and the unit of measure is wrong, so we're gonna adjust that first thing. I need to do it for all the different models that I've uploaded. So here we go, 1.695 meters. And the second thing I want to set is the wheels, these two parts, as rotating. So I'm gonna just go and pick them up, front wheel and rear wheel. Here we go. Now you can see that this is a situation very similar to what I could have in the real life. The only thing I need to put in is the speed of the rider or the wind, and put in a name for the simulation. And here I have what I'm going to simulate on. If I want to make things even more clear, explore even different yaw angles, average my results depending on what my procedure is, I can do it here. I can simulate from 0 yaw angle, even add more. Let's just say 5 and 15 or 20 here. As you can see, I can see all of those different angles here, and I can clearly understand what I'm going to simulate. All the rest are just other parameters. I can set an off ground for the ground. So in this case, if I set it to 2 meters, my motor would be flying, but we don't need that. And same way, I can decide to remove the ground or not. That's all I need to set. When it comes to deciding for what quality to go on, depending on the complexity of the geometry I'm simulating, I can decide to go for basic, standard, and pro, which basically means I'm going from 5 million cells to 30 million cells in accuracy. This is everything I need to do to be able to launch my simulations, and I click on run. Just tick the parameters to make sure that everything is set up correctly, and as you can see, I'm able to launch a simulation. Once I click on launch a simulation, everything goes on the cloud and runs over there. So the time is very short. In case of a basic simulation, in 1 hour I retrieve my results. For standard simulations, we're speaking about 3-4 hours, and for pro simulation is between half a day and 1 full day, but all simulations can run in parallel. So once I'm done, once the simulation is done, I receive a link by email that brings me to this page that is online. So all these results can be available to anyone and can be shared around just with a link to all the people that are supposed to see the simulation. And here I'll keep it very short. If you guys have questions related to the numbers that you see here, feel free to write down something in the chat. But basically we have the key metrics here in the top left corner with the drag force, lift force, coefficients, time area of course, and moments. We have a little bit of a recap of the input parameters we use to launch the simulation in case we want to replicate. We have plots with community drag and lift or punctual drag as well to understand where the drag is generated. We have a 3D viewer as well that I will leave loading up for a moment. And here in the end, we have a split view of all the slices cutting through the model to actually understand how the flow behaves around my model. And together with this, I also have the possibility of checking out the LICs. So yeah, more information on the direction of the flow. If I go to my 3D model, here is where I have most of the visual information that I might want to use. I can see streamlines, for example. So where the flow moves, I can slice them on the whole length of the model, also in different directions. And in the same way, I can check out pressure contours, so where I have most of the turbulence generated and the areas that basically I want to work on. And I can see heat transfer, I can see many parameters. Heat transfer is particularly important for the helmet. I can decide to hide the helmet and analyze the flow on the head, for example. I can do multiple things. I have friction, I have pressure coefficient, I have everything I need to know basically. So this is what we use to actually analyze every single simulation and decide how to move forward to improve the design. And this also allowed very fastly to compare different geometries and take a direction straight away already from the designing early stage that basically told us what was the best direction to follow. Fantastic. So that's all I wanted to say. I think there might be a few questions now to address, so feel free to ask and feel free to stay online just to see what happens. I would love to actually bring the conversation forward with whoever decided to join today. We have much more that we can speak about, of course, but we couldn't fit everything in a small webinar. Feel free to ask new questions if you didn't write anything yet, either on the form that was sent beforehand or on the chat right now. We're here to answer them. And also remember, if you got so far, we got a little gift for you. If you just get in touch with us and send us an email with the word mentioned here, you will get 3 additional credits, meaning that you will basically be allowed to set up and try AeroCloud by yourself and launch a standard simulation, which basically means a simulation with 15 million cells. I would be personally happy to get in touch with you and understand what your project is, what you're working on, and then planning something together to test out AeroCloud and see if this could be a potential solution for you. So yeah, that's all for today. Thank you very much, and let's move to the Q&A.